Okay, let's get started. Hello. Yeah, and as we said last week, we finished about teaching on Fourier transform, and this week we are starting into a new topic, that's Laplace transform. And so Laplace transform will be a generalization of Fourier transform, but we will see that it has many different properties, and we can use it to analyze the stability and response of a continuous time system. Okay, and I guess let's start with the Laplace transform. Okay, let's start with what is the generalization of a Fourier transform, and today we'll talk about a very different part of Laplace transform to Fourier transform is we'll talk about this region of convergence. Okay, so starting motivation for Laplace transform is we go all the way back to chapter 3. We said that in chapter 3 we said that we want to investigate the response of an LTI system, and we say that e to the st is the eigenfunction of any function. E to the st is the eigenfunction to any LTI system, and with this eigenvalue h of s. Okay? And the eigenvalue h of s can be calculated from this impulse response h of t of your LTI system in this way. So h of s equal to this integration minus infinity to plus infinity h of t e to the minus st dt. And in chapter 3 we derive this for any s. So s can be any complex number. But then later on, when in chapter 4, we use the convolution formula to show that well, small h of t and big H of j omega actually form a Fourier transform pair. And so in chapter 4, we restrict to s equal to j omega. And so we have a lot of properties derived for h over j omega. But now we go back to look at this equation, the equation 9.2. It's an equation between big H of s and small h of t. And now we think about what happens if we don't restrict s to just a purely imaginary j omega. What if we have arbitrary s and and indeed this is what we do. So this is a Laplace transform. We are going to think about how we transform this small h of t to big H of s for arbitrary complex value s. And in a more rigorous term, this is called analytic continuation. So we are trying to find so we had this function h of j omega, that's a function on real value omega, but now we try to change this omega to a complex value, and we're just trying to see what happens. Okay? So this is the definition. The bilateral Laplace transform is defined as just this integration minus infinity plus infinity x of t to the minus st dt. So t is a dumb variable, t is still real, and it's integrated from minus infinity plus infinity. And h of a, big X of s, so it's a function of this complex value s. And so independent variable, this s is not an independent variable, and it can be complex value. And for the ease of analysis, for now we will think about s. It has a real part and an imaginary part. So s has a real part sigma and the imaginary part j omega. Okay, and we have some notation here. So just like Fourier transform, we write the Laplace transform pair like this. So we have small x of t or Laplace transform to big X of s. And although we haven't proved it, we think it will have a inverse Laplace transform. So from big X of s, we can inverse transform back to the small x of t. So we write this double arrow means that the small x and the big X is a Laplace transform pair. Okay, and so this is the definition of Laplace transform with just the equation. This equation is pretty easy. You just do an integral, but now S is a complex number. Okay, and now we try to derive some of its property. First, we link it back to Fourier transform. Okay, And yeah, so you see this integration looks a lot like Fourier transform, and indeed a lot of the integration you do, you can even make back to directly Fourier transform. Okay? And yeah, so for example, if as we said, if we said S equal to J omega, then this equation is exactly the Fourier transform equation that we see a lot in chapter 4. Okay? And yeah, so x of s, where s equal to J omega, is just a Fourier transform of x of t. And yeah, so this justify our notation for Fourier transform as big X of J omega, because we so now we show that why we write this, because we think the Fourier transform is actually Laplace transform restrict to this complex value s being J omega. Okay. And now we write s as sigma plus J omega and see how this big X works like. So we kind of think big X of s is a function on this complex plane, so it has x is sigma and x is J omega. X is for sigma and x is for omega. And so we think about what's the value of this x of s on this plane. And anyway, going back to algebra, x of sigma plus J omega is, you can plug in the sigma plus J omega to your s. This is integration x of t to the minus sigma plus J omega t dt. Okay. And now a funny thing we do is now we regroup this exponential. It has e to the minus sigma t part and e to the minus J omega t part. And we group this e to the minus sigma t part to x of t. And now we look at this equation, and we see that this equation is the Fourier transform of x of t to the minus sigma t. And yeah, and the rest of the expression here is just e to the minus J omega t. So we have the integration of a function of t and e to the minus J omega t dt. So we see that if we fix some sigma, we fix some sigma value, then this value, then this equation for different omega is just a Fourier transform of x of t to the minus sigma t. So you see that you can actually just calculate Laplace transform as you calculate Fourier transform. You can just calculate Fourier transform for this e to the xt. So for some s, then you can fix this sigma, and then you calculate the Fourier transform of x of t to the minus sigma t. And then you will see the Laplace transform for that sigma and every omega. Okay. And yeah, so far is the part that the Laplace transform is very similar to Fourier transform. But as we said, there is something very different from Fourier transform. Is that x of s will have a very different convergence situation than Fourier transform. So Fourier transform, we say it's basically either converge or not converge. So Fourier transform, in our teaching, you will converge for every omega. Okay, but we'll see that x of s will converge on some s, but then diverge on some other s. And let's see this through an example. It's easier. Okay. So our favorite example, our x of t is e to the minus at of t. So this is a decaying function starting from t equal to 0. And for convenience, let's assume a is a real value that's a positive. So a is a real positive value, we have this decaying exponential. And then here we have a small reminder of this Fourier transform for x of t. So Fourier transform of x of t, you can do this integration, and you see that this is 1 over J omega plus a. And this integration only converges when a is greater than 0, because when a is less or equal to 0, then the absolute value of this thing will be constant or growing, and the integration will not converge. Okay, so this is big X over J omega. And now we think about what big X of s. Okay? And big X of s is, as we say, is e to the minus at of t, this x of t part, then times e to the minus st dt. Okay? And then this u of t, as usual, will just cut off your integration range from 0 to infinity. Then you have e to the minus s plus at t dt. And then we use the decomposition that we talked about before, so we change S to the real part and the imaginary part. So S equal to sigma plus j omega. And so this is integration. Then we have the real part and imaginary part. So this is e to the minus sigma plus at times e to the minus j omega t dt. And so this is the Fourier transform of this exponential decay e to the minus sigma plus a t and cut off at u of t as this correspondence says. Okay, and yeah, so we can look at this formula and just write down what's this Fourier transform. So we don't do the integration again, but the integration is 1 over sigma plus a plus j omega. So we have the j omega and we have the j omega, and then a becomes sigma plus a. Okay. And then now there is something actually very important here. Okay. Now we need to think about when does this thing converge. And sorry, excuse me. Where is my? Oh, excuse me. Okay, here's my pen. Okay. And now when does this thing converge? So before we say, well, this integration only converge when a is greater than 0. So this decaying part is actually decaying. And then transfer to, now we have sigma plus a here. Then we need to have sigma plus a need to be greater or equal to 0. Okay. But now sigma is part of variable, right? So a, before a was just a constant for this signal. So if you pick some a that's too large, if you pick some a that's too small, then this don't converge. It's either converge or don't converge. Sigma is part of an independent variable. Sigma is the real part of S. Okay. And yeah, so we now see that this thing only converge on some part of S. So we want the sigma which is equal to real part of S plus a equal to 0. So you move things around. You want the real part of S to be greater or equal to real part of minus a. Okay. Sorry, not real part of minus a. We assume a is real. So real part of S is greater or equal to minus a. Okay. And yeah, so our Laplace transform is actually this weird equation. So we have that this e to the minus at u of t will Laplace transform to 1 over s plus a. And we have this thing that works out only real part of s is greater or equal to minus a. Yeah. Okay, and yeah, so this is the first example of a regional convergence. We see that this exponential decay function only converge on s such that the real part of s is greater or equal to minus a. Okay. And also some example of this thing is unit step function. We can pick a equal to 0. So a equal to 0, then you don't have this exponential part, you have a unit step function. And we see the unit step function will Laplace transform to 1 over s. And with the regional convergence being real part of s greater than 0. Okay. And yeah. And also if a is positive, we see that okay, and so that is for an a equal to 0. So a equal to 0, x of t go back to unit step function, and we have this Laplace transform 1 over s. And when a is positive, then we know that then a is positive. Then we know that small x should have a Fourier transform is 1 over j omega plus a, and we see that it actually check out. So if a is positive, then j omega line is this sigma equal to 0, and in terms of complex plane, is this j omega line is inside this region of convergence. And when sigma equals 0, we have a big X of 0 plus j omega equal to 1 over j omega plus a. So they check out as the Fourier transform. Okay, any questions so far? Yeah. So yeah, big X of S is 1 over S plus a, and you pick S equal to j omega, then you have this 1 over j omega plus a. Okay. And okay, so we see that the convergence of Laplace transform is different from the convergence of Fourier transform. It don't converge on whole S plane or don't as a whole thing. It's not like Fourier transform. So Fourier transform will converge or diverge on the whole omega line. But we see that we have we have this partial convergence for Laplace transform. So this exponential decaying function, this e to the minus a u of t, will converge on the part of plane where real part of sigma is greater than minus a. So we draw it here. It's like this half plane, and when real part of sigma is smaller than minus a, then the Laplace transform will diverge. Okay. And then we see that the regional convergence is actually more important than you think. So it's not only that regional convergence is only part of plane. It's also that it's a very important part of the Laplace transform as we will see in this example. So we now consider a different function, and it's a Laplace transform. So we have a small x of t equal to this minus e to the minus at u of minus t. Okay, so this is a weird function. We'll very soon see why we pick it, but like this. But if you want to plot it, it's a function that only has value for t less than 0 because of this u to the minus t. And then this e to the minus at part, it has different form depending on whether a is less than 0 or a is greater than 0. So if a is less than 0, it looks kind of like this. It's decaying to minus infinity. And if a is greater than 0, it is exponentially growing to minus infinity. Okay. So this is this weird function on weird exponential function on negative t, and we can calculate its Laplace transform big X of s by just plugging in the formula. So minus integration minus infinity to plus infinity e to the minus at. So this is minus sign go to this minus sign, and then we have u of minus t, and e to the minus st from the Laplace transform formula. And this u of minus t will cut off the upper bound of your integration to 0. Okay. So we have this minus integration minus infinity to 0, then e to the minus s plus at dt. So then we have a here and s here, so p on s plus a. And if you do this integration, you will see that once again you get 1 over s plus a, assuming your integration converge. Okay. Yeah, you see you have just an exponential function, and the integration of exponential function is pretty easy. You have 1 over this coefficient here, and all the negative sign will cancel out, and in the end you will get this 1 over s plus a. And now we need to, but this is when the integration converge, and we need to think about when does this integration converge. And this integration is from negative infinity to 0. So it's extending to negative infinity, so we want this thing to be decaying to negative infinity. That means the real part of s plus a need to be real part of s plus a need to be less than 0, like this. Let me see. Yeah, real part of s plus a need to be less than 0, and that means the real part of s need to be less than minus a. Yeah. And so we see that this this weird function minus e to the minus at u of minus t will Laplace transform to 1 over s plus a, and it only converge on real part of s is less than minus a. Okay? And now something very weird happens. So we look at now we think back to our example 9.1. We see that example 9.1 is e to the minus at u of t. Will Laplace transform to 1 over s plus. It will also transform to Laplace transform to 1 over s plus a, but with the regional convergence being real part of s is greater than or equal to a. Then we see that we have two very different functions, but they will Laplace transform to the same thing. They both Laplace transform to this 1 over s plus a. Okay, and the only difference to their Laplace transform is that they have different regional convergence. So in our example 9.1, is regional convergence is real part of s is greater than minus a, and example 9.2, Oh, sorry. Sorry. I missed up those two. So example 9.1, we have a regional convergence is greater than minus a, and then in example 9.2, we have a regional convergence being less than minus a. Okay. And because they transform from different functions, so we want they transform from different time domain function. So we want to have a different frequency domain Laplace transform. But we see the algebraic part is the same. They are both 1 raised plus a. And the only difference between them is this regional convergence. And then, so from here we see that the regional convergence, the set of values of S which the integration converge, is actually part of information about your Laplace transform. It's a very important part of information. Okay. And as we said, this is called the regional convergence. So the regional convergence is the range of value of S in which your integration actually converge. Okay. Okay. Yeah. And once again, so this is a very important concept. So let's say this is the third time. So we see that we have these two very different time domain function. One of them only have value on positivity, one of them only have value for negativity. And turns out that when we do this equation 9.3 integration, they give you the same algebraic expression. This is 1 over S plus a, but they have different regional convergence. So the example 9.1 have a regional convergence. Look at this. It's the part where the real part of S is greater than minus a, and example 9.2 is a totally different regional convergence. And it says this shading part as a regional convergence is when S is real part of S is less than minus a. Okay. And let's emphasize once again, ROC is an important part of the Laplace transform. And so you write down Laplace transform for some function, then you need to specify the ROC, and this will happen in on your homework problem and all your exams. Whenever you write down a Laplace transform, you need to specify the ROC, because this is a very important part of information about your Laplace transform. Okay. Once again, because if you omit the ROC, then you see the algebraic part don't give you a unique time domain function. So if you want your Laplace transform to correspond to a unique time domain function, you need to specify the ROC. Okay, any questions so far? This is the most important thing about this chapter and next chapter. That is your Laplace transform. You need to write down this region of convergence ROC. Okay, and Okay, and later today we'll talk more property about this ROC. Okay. And for now, let's just look at more examples of Laplace transform. Let's go back and while also seeing some property of ROC. So let's think about the Laplace transform of this function. So this is just a linear combination of two of the exponential 9.1. So a linear combination of two exponential decaying function. So you have 3 times e to the minus 2t, then minus 2 e to the minus t. Okay, and I would say this is a linear combination, and we use the equation 9.3 to do Laplace transform. Then we see, because this integration is linear, so this is just 3 times the Laplace transform of e to the minus 2t minus 2 times the Laplace transform e to the minus 2t. And then the integration is easy to do. So this integration is just linear. So we have 3 over s plus 2 because there are minus 2 here, then you have plus 2 here, and minus 2 from this minus 2 from this minus 2, and s plus 1 where this 1 is from this e to the minus t. Okay. So algebraic part is easy, and now we need to think about the ROC part. Okay. And so individually, we know these two parts have their different ROC. So, so this example, we have that e to the minus at u of t Laplace transform to 1 over s plus a, with region of convergence being real part of S greater than minus A. And yeah, so these two parts both satisfy this form. And so the first, okay, so we have a different order. So the second part, e to the minus t u of t, will have region of convergence being real part of S greater than minus 1, and this e to the minus 2t u of t will have region of convergence RES greater than minus 2. And now we think about what's the region of convergence of a linear combination of them. So we want the integration to converge on both parts, and so what we have is we want our S to be inside both of these region of convergence. So basically, we want the intersection of those parts. And so we take a smaller of them, that's the real part of S greater than minus 1. Okay. So we see that is e to the 3e to the minus 2 tu of t minus 2e to the minus tu of t will Laplace transform to this equation. That's it, just multiply all this expression, and the region of convergence is RES greater than minus 1. Is the intersection of these two regions. Yeah, and similarly we can have another example. So x of t is e to the minus t 2t u of t, and we have a more complicated function here, e to the minus t cosine 3t u of t. But we can just break cosine into a linear combination of complex exponentials. So cosine 3t has this e to the 3jt term and e to the minus 3jt term. Okay, so you break cosine equal to this summation of e to the minus 3t and e to the minus e to the 3jt and e to the minus 3jt, and you combine with this e to the minus t, so you got this e to the minus 1 minus 3jt and then e to the minus 1 plus 3jt. Okay. So once again, you get a whole bunch of complex exponential, and now we need to go back to 9.1 a little bit. So we look at 9.1. So although we derive 9.1 as having a real value a, but we recreate all those equations, we find out that all those equations still works out, and the only thing you need to change is that this RES greater than minus a, you need to change into RES greater than minus REA, okay, for this integration to converge. Okay. And now let's go back to this example, and go back to this example, and once again we can do this integration, and we have these three parts that algebraically Laplace transform to 1 over s plus a, with a equal to 2, and this 1 minus 3j and then 1 plus 3j. And then the region of convergence will be RES greater than minus a, and so minus a was minus 2 here, and here minus a we only care about the real part, so RES greater than minus 1 here, and RES greater than minus 1 here. Okay. And so once again we have this linear combination of these three part Laplace transform, and we want all three of them to converge. So we want this integration to converge. So we basically want all three parts to converge, and so we need to pick the smallest the intersection of the region of convergence here, and that will be RES greater than minus 1. Okay. And the algebraic part is this, and if you want to combine the terms, then it will look like this. Okay. And here so here are some examples of Laplace transform. Any questions so far? If not, then we digress a little bit to talk about rational function. Okay. And so far we have seen that our Laplace transform has a particular form that is they are rational functions. That means that our big S of S can be written as some polynomial of S, divided by some polynomial, another polynomial of S. So I have n of S, n as n for numerator, and d for denominator, d of S. Okay, and we have seen, so here we have a small review. So I have seen this form of rational function before in chapter 4 and chapter 5. Remember, chapter 4 we have some Fourier transform as the rational function of j omega, and in chapter 5 we have the Fourier transform as some rational function of e to j omega, and then what we have a rational function is we have big H as a rational function because it's big Y divided by big X, and when we solve those linear equations, it's summation B terms over summation A terms. Okay, so this is a small reminder of what we have seen, what kind of rational function we have seen. Okay, but anyway, back to Laplace transform. So a lot of Laplace transform we will see are also rational functions. So although not every Laplace transform is rational, but a lot of Laplace transform will be rational, and will be those rational Laplace transforms will be a very important part of functions we study. Okay, and yeah, and for example, as we see, if x of t is a bunch of complex is a linear combination of complex exponentials, then our big X of x is rational. Yeah, and also as those examples in chapter 4 and chapter 5, we'll see that if we have a LTI system specified by those linear differential equations, then the system function, this big H, will also be rational. Okay. So rational functions are very important, and we'll analyze these rational functions by looking at the roots of these two polynomials. So we have a polynomial n and a polynomial d here, okay? And the roots will be very important to our analysis, and we want to mark them on the complex plane. Okay? So roots of n will be, this is the value of s where n of s equals 0. Will also be the value of s where big X over s equals 0, and they mark as this O mark as O on the complex plane, and root of d. So the value of s where d of s equals 0. There will also be the value of s where big X of s equal to infinity. So those are poles of big X of s. They will mark with this cross on the complex plane. So for example, we have example 9.3 and 9.4. The equation are written here, and we have the ROC and the poles of zeros marked on the complex plane here. So this is example 9.3. So we see the ROC this real s greater than -1, and it has a 0 or x -1, so it has a 0 of 1 here, and the two poles at the -2 and the -1 marked as close here. And example 9.4, it has the algebraic expression here, and ROC is RES greater than -1, so marked as a shaded region here, and it has two zeros marked here. We don't have the exact value of 0, but they are here. And it has three poles at the -2, and there's -1 plus 3j, and -1 minus 3j. Okay, so that's a pole zero plot and the ROC of some Laplace transform, and those are also the kind of thing you will do in homework. So we'll ask you to write down Laplace transform or something, and ask you to draw the ROC and mark the pole and the zeros of your Laplace transform. Okay, and also sometimes it's so now we go to a bit of more theoretical analysis part. So sometimes we will also look at the point 0 at infinity. So we think when x go to infinity, whether x of s go to 0 or infinity. Okay, and when it go to 0, okay, so we have infinity first. So if the order of n is more than order of d, then when s go to infinity, big X of s also go to infinity. So we think we think big X of S has a pole at infinity, and the pole has orders that depend on whether how many orders does n of S exceed d of S. That number we say is k here. And on the other hand, if order of d is more than order of n, then when s go to infinity, the big S of S actually go to 0 because they have 1 divided by infinity. And yeah, so we have we say big X of S has k zeros at infinity. Yeah. Okay. So this is our analysis at infinity. And let's go back to more example about Laplace transform. So here we have the linear combination of 3 parts. So 2 of those complex exponential we have seen quite a lot, and delta function. Okay. And the Laplace transform of delta function we haven't seen before, but it's pretty easy because the integration around delta function is always pretty easy. So integration minus infinity plus infinity delta of t e to the minus t dt. But by the filtering property of delta function, it's just set t to 0. So you have a e to the minus s times 0. And that is 1 for every s. Okay. And we see that this integration works out for every s. So the RC for delta of t is actually very nice. It's the entire s plane. Okay. So this is more like Fourier transform where when you converge the whole domain, whole domain of S converge. Okay. But anyway, so we have RC being this, and now we also Laplace transform the excuse me. We also Laplace transform the other 2 parts, and we see that this e to the minus t give you this 1 over s plus 1, and this e to the 2t give you 1 over s minus 2. And they have different RC, and so the first part, this e to the minus t has RC. We also have the RC value here, RC greater than minus a. So this has RC real part of S. Let's skip the real part of S. So this has RC real part of S greater or equal to, so a equal to 1 here, greater equal to minus 1. And this has RC greater or equal to 2 because a equal to minus 2 here. Okay. And yeah. And now we compare those 2 RC, then we see the real part of S greater or equal to minus 2 is the stricter one. So the total RC for this big X of S is dominated by this term. So this is the real part of S greater or equal to 2. Yeah. And then we can try to write this as a rational function and find all its root and zeros. Those we see is 1 minus s minus 1 squared over s plus 1 times s minus 2. So we have so we see we have 2 zeros at s equal to 1 from this s minus 1 squared. So we draw it as this double zero like this here, and it has a root at s equal to minus 1 and a root at s equal to minus 2. And also RC is this RC is this real part of s greater or equal to minus 2. Okay, and yeah, I think we are quite on schedule. So let's take we can probably stop earlier today, but let's take a break now and come back in 10 minutes. So we come back at say 4:20, and then we'll talk about those A properties of RC. Okay, yeah, let's take a 10-minute break until 4:20. Okay. Okay. Hello. Let's go back. Yeah. And from this class we talk about the definition of Laplace transform, and we have talked about we found out the Laplace transform, different from Fourier transform, has this concept of region of convergence, and it's a very important thing for Laplace transform. It's an important part of information of Laplace transform, and here we are going to talk about the properties of ROC. Okay, and so first property, this is the most important property. It says that the ROC of x of any x of s or any Laplace transform consists of strips parallel to the j omega axis in the s plane. Okay. So so it will be set of some lines. Okay, so so what does this actually say is that whenever some point is in ROC, then this whole line of the same sigma will be inside ROC. And really, this property comes from a property of Fourier transform that we didn't explicitly prove, but we assume that the Fourier transform will either converge or diverge for the whole omega line. Okay. and we say x of sigma plus j omega correspond to the Fourier transform of x of t to a minus sigma t at some sigma. Okay, so at some fixed sigma, then this whole line of different omega correspond to Fourier transform of x of t to a minus sigma t. Okay. And because the Fourier transform either converge or don't converge for every omega here, so this line is either inside ROC or not inside ROC for your Laplace transform. Okay. And then we also have a property 1.5, and now this is be more sketchy. Okay. And it says that then ROC of x of t. So we know to think about when does this x of t to a minus sigma t has a convergent Fourier transform, and we say it's when this thing is absolutely integrable. So we think the Laplace transform is convergent only if this minus infinity plus infinity absolute value of x of t times e to a minus sigma t dt is a finite value. Yeah. And yeah, so this is kind of property 1.5, which we will use even more than property 1, is that so some vertical line on sigma is inside the ROC of your Laplace transform if only if this equation holds. And yeah, I guess the motivation for this is that remember this is one of the Dirichlet condition. But if we say this, then for those of you who remember what are the Dirichlet conditions, you remember that there are actually 3 Dirichlet conditions, and this is only one of them. And here we just hand wave through this and say that we ignore those x of t that might satisfy this, but violate the other 2 Dirichlet conditions. And then we just look at the more quote-unquote more reasonable x of t, and we think whenever this satisfies this absolutely integrable condition, then it has a convergent Fourier transform. Okay, and so that's kind of how we derive property 1.5. Says that some place is inside ROC if only if this integration is convergent. Okay, this is the first property, and this tells us how to find whether it tells us basically this property tells us how to find ROC. So ROC will be a collection of those strips, and strip is inside ROC if only if this integration is convergent. Okay, and so that's the first property is quite of a reasoning behind it. And second property, now this is actually a very easy property to derive, but very useful. It says that yeah, so for rational Laplace transform, the rational Laplace transform has those point zeros. Let's go back to a bit of a reminder. So where is it? Okay, I think it's here. Yeah. Yeah, so remember we say that a lot of Laplace transform is those rational function, and the rational function we can plot those zeros in the poles. And for those zeros in the poles, one important property is that of ROC is that ROC should not contain any poles. And this is very easy to derive because by definition x of s is divergent on poles x of s infinity. Then obviously that means the integration doesn't converge, and the Laplace transform integration does not converge at the poles. So poles should not be inside ROC. Okay, so that's easy to derive property, but pretty important. And then now we think about now we have about 4 properties that tells us about the shape of ROC. Okay? And the first property says that for a lot of functions, the ROC is actually an entire S-plane. So the Laplace transform actually converge very nicely on areas. And that's for when x of s is of finite duration and is absolutely integrable. Okay. And that means x of s kind of look like this. Okay. So it's something finite duration, and also the value is pretty finite. It's absolutely integrable. If x of s, sorry, not x of s, it's x of t. So if the x of t is something like this, it's quite a finite function over a finite interval, then our Laplace transform will actually converge on every s. Okay. And why is that? Because now we see why this property 1.5 is important. Now we want to think whether some sigma is convergent is inside your RLC. They want to check whether this integration of absolute value of x of t times e to the minus sigma t dt, whether this is convergent. Okay. And yeah, now we think about what is x of t times e to the minus sigma t look like. So x of t look like this thing. And now we are multiplying it with e to the minus sigma t with real value sigma. And so sigma can be positive or negative. If sigma is positive, then this e to the minus sigma t is exponentially decaying function, and sigma is negative, we have an exponential growing function. Then we have our x over t multiplied by those exponential decay or exponential growth, and this function kind of look like this. Okay. And then the important thing, we want to show that those kind of things will always be absolutely integrable. Okay. And just by those two pictures, you can kind of feel it's absolutely integrable, because basically this thing is basically x over t, but multiplied by the most e to the minus sigma t1. So you see this exponential function. It has this exponential decaying function. Its highest value is this e to the minus sigma t1. And then if the sigma is less than 0, then this is at most e to the minus sigma t2. But t1 and t2 and the sigma are finite value for any finite sigma. And so you are basically multiplying x over t with some finite value, and so this integration should be still finite. And we can see all those reasoning in algebra more clearly here. So we start with our x over t has some finite duration, and also it's absolutely integrable. So this integration is a finite value. Yeah. And now we can do case analysis for, now we want to check whether this is finite, whether this x over t now multiplied with e to the minus sigma t has this integration being finite. Okay. And so we have those two cases. We have a case of sigma positive and sigma negative. And for sigma positive, we see that this HR e to the minus sigma t part is at most e to the minus sigma t1, because this picture shows this exponential decaying function is at most e to the minus sigma t1. And because of that, then this integration is at most e to the minus sigma t1 times this original integration. And so this is a finite value. So we see that for every real part of x greater than 0, they are inside RLC. And also similarly for negative sigma, this integration is less than e to the minus sigma t2 times this original integration, and so this is also finite value. So every real part of x less than 0 is inside RLC. And I guess if you are really picky, we can also check that. And we also verify that when sigma equals 0, this integration is finite, because when sigma equals 0, it's just this original integration. Okay, and so we see that for every value, for every value of sigma, the integration is finite, and so every s for every sigma, the s is inside RLC. Okay. So yeah, the entire S-plane is in RLC for this finite duration interval, and also absolutely integrable. Okay. Any question about the derivation here? Basically, we check this property 1.5 and see that for every sigma, if our x over t is a very well-behaved function, then for every sigma, this integration will be finite. Okay, so that's property 3. And then I'll go to, okay, so those property, Okay, so let's go to an example of this first. So we have x of t equal to e to the minus at, so it's kind of like example 9.1, but with a cutoff. So we have x of t equal to e to the minus at between t from 0 to big T. Okay, so kind of like this thing. And I plot this for a greater than 0, but this thing is actually convergent for ABA. Okay. So x of t is the exponential function from 0 to big T, and it's just 0 otherwise. Okay. And then we can calculate our big X of s, and the integration is pretty easy. So e to the minus at, e to the minus st dt, and then you just get this 1 over s plus a, and then two bound of this e to the minus at, e to the minus t. So at 0, this thing is 1, and at big T, this is e to the minus s plus a big T. Okay. And yeah, so you can just do this integration, and it's easy to see that because you have no infinity here, this integration is convergent for ABS and the ABA. Okay, and I guess there is something extra. Okay, so the integration is convergent for every S and A, but if you look at this formula, then you look like there is a pole at S equal to minus A, because you have 1 over S plus A here. But actually not a real pole at S equal to minus A, because this 1 minus e to the minus S plus at is also 0 when S equal to minus A, because you have 1 minus 1 here. And to check that what's the actual value of x of s at s equal to minus a, we can use the L'Hopital rule. If you still remember calculus, and you take the differentiation of both the upper side and downside with s, and then take s go to minus a. Okay, so you do differentiation, then the lower part just become 1, and the upper part become this, so 1 differentiation goes away, and then you have this is minus t, so s is coefficient minus t here, so minus t cancel with plus t become t, and just have this e to the minus s plus at. Okay, and then you take s become minus a, then this exponential part cancel out, then you have x of minus a equal to t. And you can also check that from the integration here. So when x equal to minus a, you are just integrating 1 here. So you just have 1 integration over this period of from 0 to t. Integrating over this interval from 0 to t, and so integration should be just big T when s equal to minus a. Okay, and let's check out. So we see that the x of s does not really diverge at s equal to minus a, don't really have a pole. And so your x of s is 1 over s plus a times 1 minus e to the minus s plus at, and this is convergent on any s. Okay, and so this is truncated exponential function. Okay, actually convergent everywhere because it has a finite duration. Okay, and the next property is when x of t is a right-sided function. Yeah. And so this is like a handful of finite duration functions. And so right-sided function, we have an example here. So it's a function that extends to a right maybe to infinity. May or may not extend to infinity, but it has a cutoff at here at t equal to t1. So on the left side there is a cutoff. This is a right-sided function. On the left-hand side it has a cutoff at t1. Okay? And so if x of t is a right-sided function like this, and then RC will extend to infinity to the right side. Okay. So right-sided function, RC will extend it to also extend to infinity on the right side. And to express that more logically, we say that if sunlight at sigma 0 is in RC, then everything to the right is also inside RC. This is a right-sided function. So So it has a cutoff at the left hand side, and then we extend to the right hand side. Okay. And I think the intuition is pretty easy. So we think about what happens when you are. So once again, we want to check this integration of x of t to the minus sigma t, right? Of x of t to the minus sigma t. And so if this integration is convergent on some sigma 0, means that this thing times the exponential decaying function of coefficient sigma 0 is convergent. Then we make a sigma 0 even larger, then this thing will decay even faster. And so this exponential function will decay even faster to this plus infinity in t. So this thing will be more convergent. Okay. And yeah, we can write down those intuition as algebra here. Okay. So if the integration with sigma 0 is finite, then then the integration with some sigma t1 will also be finite, because it will be less than it will be integration. The integration will have a difference is minus sigma 1 plus minus sigma 1 minus sigma 0 t, and this sigma 1 minus sigma 0 t is an exponential in decay function. And so to the plus infinity, this will be go to 0, and but this thing might be, so this function, this difference part might be bigger than 1 when t is less than 0, but we see that the most negative t can be only t1, so here we use this cutoff at t1. So the difference between sigma and this exponential difference between sigma 1 and t1, sorry, sigma 1 and sigma 0 can be at most this e to the minus sigma 1 minus sigma 0 t1. And yeah, so this is a finite value because t1 is a finite value, and so this integration is finite. Okay. And yeah, here is a bit of a picture that talk about the intuition. So we have exponential decaying on e to the minus sigma 0 t, and then we have done sigma 1 bigger than sigma 0, so it's exponential in decaying even faster. So the integration on the positive t part will be even smaller, and on the negative t part is bounded by at most those difference at t1. The difference at t1. Okay. And yeah. And so this is the right-sided function, and then the next property you can probably guess, so it's very similar is for the left-sided function. So left-sided function is actually defined by some function has a right-sided cutoff. So on the left-hand side it can be arbitrary extent, but on the right-hand side it has a cutoff at t2. Okay. So for if your function has a cutoff at the right-hand side at t2, then your RC must extend to negative infinity. That means that, so your excuse me, yeah, so your RC must extend to the left-hand side to infinity. Okay, so that means if some point is inside, some point sigma 0 is in RC, then every point to the left of sigma 0 is also inside RC. And the proof is very similar, so let's don't run through the proof again. You just switch base 11 and right. So you have this, you have exponential decay on sigma 0, and then you have more negative exponential decay. Sorry, exponential function. So with sigma 0, that decay into minus infinity, and then if you have more negative sigma 0, you will decay to this left infinity even faster. Okay, and then the next part we combine basically both property 4 and 5 to have the property 6. Okay, so now we have basically arbitrary x over t. So x over t is two-sided. Then excuse me. So if x over t is a two-sided, so basically an arbitrary function, then our RC will be a strip. Okay, So the important part here is this A here. So the RC will be at most one strip. So RC may not exist, but if there is an RC, there will be one continuous strip. And in particular, so RC cannot be two strips like this. Okay. And so RC most of the time will look like this strip, this strip here, but sometimes it still extend to infinity. Let's ignore that for now. Okay. And so the intuition here is that we have a two-sided function, so extend to positive infinity and negative infinity. Sorry, positive infinity and negative infinity. Then we can cut this function into two parts. So we pick an arbitrary point t0 here, and we cut this function into a right-hand part and left-hand part. So right-hand part is a function as O0 when t less than t0, and then whatever x over t is here. And the left-hand part is x over t until t0 and 0 here. Yeah. And then we can use our property 4 and 5, and we know the right-hand part has ROC to extend to the right-hand side, and then the left-hand part x of L has ROC extend to the left-hand side. Then our x over t is the linear combination of xr and xl. So the RC should be the intersection between this thing and this thing, and the intersection of those two things will become a strip if they have overlap. And yeah, but because this extends to plus infinity, this extends to negative infinity. So you see that when they have the overlap between them, the overlap can be just one strip. So there will be no two strip. Okay. And lastly, example of this overlap. So our x of t is this e to the minus b absolute value of t. And b can be positive and negative, and we plot them here. So when b is positive, we have this double-sided exponential decaying function. So yeah, e of minus bt look like this. So when t is positive, is exponential decay. When bt is negative, it's also exponential decay. And when b is negative, then we have this double exponential growing function. So yeah, like this. Okay. And as we said, then we can analyze what the ROC of this function look like. And obviously, a good choice to pick t0 is pick t0 equal to 0. So we break into this positive t part and negative t part. So positive t part, we have this e to the minus bt, and we cut off t equals 0, so u times multiply with t of t. And negative t part, then this absolute value of t become negative t, so we have e to the plus bt, and cut off by this u of minus t. Okay, and then we can have a Laplace transform of both those two parts. And we can do integration, but we already do the integration. So e to the minus bt, we have done the integration on example 9.1. It is Laplace transform to 1 over s plus b with the ROC being real part of s greater than minus b. And also the other thing, we also then the other equation, the other part, we also do very similar Laplace transform before. Okay, so that's example 9.2. Example 9.2, we have this e to a minus e to a minus bt u of minus t Laplace transform to 1 over s plus b, and with the real part of s less than minus b. Okay, so we change put the h1 negative sign on b, so plus b from go to negative b. So every b become negative b here. So this plus b become negative b, and this minus b become positive b. And also we have h1 negative sign, so we have h1 negative sign here. Okay, so those are the two Laplace transforms. So 1 over s plus b and minus 1 over s minus b, and more importantly, we have ROC being minus b, and the real part of s greater than minus b, and the real part of s less than plus b. Okay. And now we can analyze the two cases. So we want to see whether what happens when b is less than 0 or plus or b is greater than 0. So when b is less than or equal to 0, then we can have the intersection between those two ROC. Okay, so I think this is this part. So b real part of s is greater or equal to negative b and less than or equal to plus b, and so it has this intersection between negative b and positive b. Okay, and then the algebraic part is just this part plus this part. So once again, it's a rational function. It's this minus 2b over s squared minus b squared. And then when b is greater than 0, then we actually see that the ROC has no overlap. So we want the ROC to be greater or equal to negative b and less than positive b. But negative b is greater than positive b, so the ROC has no overlap, and so this thing actually has no Laplace transform. This function has the Laplace transform is divergent for ABS, and you can kind of feel it because this is a very divergent function. Okay. And on the other hand, this thing has convergent Laplace transform between minus b to positive b. Okay. Any question on this example? So we show that we have this two-sided function. So this function extends to positive infinity and negative infinity, and its ROC is a strip because its ROC is the intersection between the ROC of the right-sided part and the ROC of the left-sided part. Okay, and that's an example, and then let's go to the list two property of Laplace transform. So those two properties are related to rational functions because we are talking about poles. Okay, so if we have some rational function x of t and it has some poles, then ROC will be bounded by the poles or extended to infinity. Okay, and then in additional poles in C side ROC, this second one is just property 2 we'll talk about. But we have another property, so the ROC is bounded by the poles of infinity. And we don't really have proof here, but this is, I guess we will have kind of a proof later when we talk about the Laplace transform of a rational function, but for now it's just stated here. Okay. So for example, here we have rational Laplace transform, and we see that its ROC is indeed bounded by the poles here. So it's one of the edges is point minus b, and one of the edges is this point positive plus b. Okay, and so that's property 7. Okay, and property 8. Property 8 is just combining property 7 with the previous properties. Okay, so it says our x of s is rational, and if small x of t is right-sided, then we know that. Okay, so that gives us a draw picture here, and we know that if x of t is right-sided, then ROC should extend to positive infinity. Okay, so the right side of that strip should go to positive infinity, and then the left side of the strip should be bounded by a pole. Okay, assuming this thing has a pole. So if x of t is right-sided, then your ROC will be right-sided of the rightmost pole. Okay, and similarly, if your x of t is left-sided and you have a whole bunch of poles, then your ROC should extend to left negative infinity, and on the right side it should be bounded by the leftmost pole. Okay, and so that's property 8. Tells you what the form of ROC should look like for rational function, functions. Okay, and then next I think we have the next example that we'll actually see quite a bit in this chapter. We talk about how to calculate, basically we talk about how to calculate ROC of a rational function, or kind of an inverse Laplace transform of a rational function. Okay. But anyway, for now just think about what are the possible ROCs for a rational function. Okay. So we have a rational function x of s equal to this 1 over s plus 1 times s plus 2. Okay, so this thing has a pole at -1 and -2. And then we do a thing that we have done in chapter 4 and chapter 5 a lot before, that is partial fraction expansion. Okay, sorry, partial fraction decomposition. So we write this 1 over s plus 1 times s plus 2 as 1 over s plus 1 minus 1 over s plus 2. Yeah, and anyway, we look at this pose on the s-plane, and then we know it's a rational function. So from property 7, then we know that there are only 3 possible ROC that we can have for this big S of S. So we know the ROC should be a strip, and the ROC should be bounded by the poles. And so there are 2 poles, so there are 3 possible ROC. So you can have a ROC that's from the rightmost pole to right infinity, or you can have a ROC that's inside in between those 2 poles, or you can have a ROC that left to the leftmost pole. Okay, and and also from the property that we talked about before, we know that this function, this ROC with this x of s should correspond to a right-sided function. And this ROC, because it extends to left infinity, it should correspond to a left-sided function. And then this ROC should be correspond to a two-sided signal, two-sided function. Okay. And and also there is a extra property, and we can also think about whether this function has a Fourier transform. And remember, Fourier transform is this is not quite a property, but the nice thing to remember for ROC is the Fourier transform correspond to sigma equal to 0. Laplace transform is sigma equal to 0. So Fourier transform correspond to the Laplace transform on this purely imaginary axis on this j omega line. Okay, and so whether the ROC including this j omega line determines whether the time domain function has a convergent Fourier transform. Okay, so this function should have a convergent Fourier transform, and those other two functions should not have a convergent Fourier transform. And so here we skip a little ahead. So later on we will see we do inverse Laplace transform, and we see that to do inverse Laplace transform we do partial fraction expansion, and this first one will be, let's see, yeah, and we'll have 4 different possibilities for the inverse Laplace transform. Okay. And one of them is non-convergent, and so I think the first one correspond to a right-sided function, and they correspond to this ROC, and then the second one correspond to a left-sided function, it correspond to this ROC, and the next one you will have a two-sided function, you will correspond to this ROC. Okay. Basically, each partial fraction here has 2 possible ways to pick ROC. Okay, and but that's actually a later material for inverse Laplace transform. And for now, we can just look at this and know that those two poles for rational function tells us that there are 3 possible ROC for Laplace transform. Okay. And I think that's enough teaching today, and we are quite ahead of schedule, so we can stop early today. And yeah, next time we'll talk about inverse Laplace transform, and you can probably guess that because ROC is very related to the Laplace transform. So when we do inverse Laplace transform, the ROCs will also be a very important concept. Okay, so let's stop early today, and let's see if anyone has any question. Yeah, anyone has any question, then you can come over after class. Okay, so see you on Thursday.